Hi, everyone. Wanted to do a couple quick rigid body, well, not quick, it'll take us how long it takes. Want to do a couple rigid body equilibrium problems and just see if we can have a little more time to try these out. So we have this system and we see that it actually has two supports, which have an AX or an AY and an AX component, and a dy and a dx component, and those are because they're pins and they have reactions. We see DC, and if we actually start looking for, we can actually know that DC is a two-force member. So DC has pin reactions. We assume that it's weightless, and therefore the force in member DC is going to be aligned with member DC. That's a little bit tricky, so we're just going to keep looking for those and playing around with that. Let's see if we're looking at this thing. We know that this angle right here is 45 degrees. How do we know that? Well, because 1.5 meters and 1.5 meters, it's an equilateral right triangle. All right, so if we want to answer what's the force in member DC, the magnitude in AX, and the magnitude AY, what makes sense to section? Where do we want to cut this thing and make a free body diagram? Well, if we want to know force and member DC, AX and AY, we want to probably have something that looks like that, where we cut that beam away and replace it with its forces. All right, cool, let's do that. All right, there we go. So we have AY, AX, so when I do free body diagram, I do BAFA or BAFAD, so where you have our body, our axis, I'm defining with our y and our x component. That just means I'm doing something like that. Our forces, we draw in the forces of the reactions, what they could do. We don't assume they're zero until we do the calculations. Then we know that this bar, CD, is pushing with a force, and we have that applied force of 4 kilonewtons. All right, now we can have angles. We said that that angle is 45 degrees there, so let's put that one in there. And we can add some dimensions. Those might help us out. All right, so most students like to start with some of the forces in the x direction. So what are the sum of our forces in the x direction? Well, we have AX going to the right, and we have FCD going to the right. And so yeah, that's FCD times the cosine of 45. They both act positive. Okay, great. Which just means that AX is going to be the negative of FCD times the cosine of 45. All right, we know what those two are in relation to each other, but we don't know what either one is, so we got to do another one, another equation. So we say, all right, let's do forces. We're used to forces. Sum of the forces in the y equals 0. All right, so we have AY going up. We have FCD going up, and that's FCD sine 45. And then we have 4 kilonewtons going down. So we can put AY in terms of FCD, but we don't know what either one of those are. So here's why it's sometimes nice to start with moments. So if you take the moment of our point A, first of all, how did I know to take the moment at point A? I take the moment at point A because I want to, number one, it gets rid of AY and AX because those two forces go right through A, so neither of them have a moment. And point A, therefore, takes FCD and puts it in terms of a 4 kilonewton force. And it's just kind of cool how that works. So what portion of FCD is acting to rotate? Well, it's this FCD times the sine of 45. FCD times the cosine of 45 goes right through point A, so that component actually disappears. That's cool. And that's acting at 1.5 meters. And that's going to be a positive moment because we apply our fingers with our FCD sine 45. We point them in the same direction and we put our palm facing point A, and we see that that's going to be positive. Now our 4 kilonewtons is going to be, we put our fingers facing our arrow, or in the direction of our arrow, our palm facing point A, and we see that that's acting at 1.5 meters plus 1.5 meters, so that's 3 meters. So what do we end up with? We end up with FCD times the sine of 45 times 1.5 meters, and that's going to be positive. But we see that when we align our fingers with our 4 kilonewtons and we face our palm towards point A, we see that 4 kilonewtons times 3 meters, which is 1.5 plus 1.5, is actually going to be a negative moment due to the right-hand rule. And what's nice is, boom, we can solve for FCD right now. So FCD is FCD's times the sine of 45 times 1.5 meters, and 3 times 4 is 12. It's minus 12 brought over to the other side, so that becomes positive. We do a little math and we see FCD is equal to FDC, and that's 11.3 kilonewtons. So the answer to our first question is E. All right, so what's the answer to our second or third questions? Well, now that we know FCD, we can answer either one. Let's, well, Y is closest, so let's try that. So we know AY, we move FCD over to the other side and 4 kilonewtons over to the other side. The SIGN sign switch, so minus FCD times the sine of 45 plus 4 kilonewtons minus FCD is minus 11.3 times the sine of 45. That's about 8, but that's negative. So minus 8 plus 4 is minus 4. So the magnitude of AY, that would be C. And so AX is, we look at some of the forces in our X. So FCD times the cosine of 45 is minus AX. AX is minus FCD times the cosine of 45. FCD is 11.3. Cosine of 45 is 0.707. We multiply those two together and we get AX is about 8. And we're just caring about the magnitude. But we actually see that we guessed wrong. Our sign's wrong. Our SIGN's wrong. No big deal. All right, so let's try another one of these things. All right, so now we have this bar and we have some questions. So the first things first, we should be thinking about what questions we want to answer because that informs what we section for our free body diagram. So first question, the tension at B is blank the tension at E. Huh, that's a good question. It's a rope. It's a rope going through a pulley. We're not told that friction's part of our system. Tensions are equal. So the tension at B is actually equal to our tension at E. Okay. Now the next question is a little more tricky. The magnitude of the moment at A due to this tension at B, so let's call that T, is blank the moment at A due to the tension at E. All right, so I think we need a free body diagram. Let's cut this thing. All right, let's draw it out. So what's our free body diagram look like? So we have a pin that can resist in 2 degrees of freedoms. Let's use AX and AY, and that will actually define our X and Y coordinate system. Okay. We have our body, our axis defined by our AX and AY. That's a short, easy way to do it. Our forces, well, we have our tension at B, our tension at E, and then we have this 5 kilogram weight at C. Okay. And then we can write in our angles if we want. Well, we already have 53 degrees and we use our inverse tan to help up with that. And then we can add in that these are 2 if we want. All right, so what's the moment at B? The magnitude of that moment at B is tension times 2. Tension times that distance, which is 2. Force times a perpendicular distance. All right, so what's our moment at E? Well, the perpendicular distance is 2 plus 2 is 4, so it's 4. And what is that that vertical component of that t at E? Well, that's t times the sine of 53, little trig. Sine of 53 is actually 4/5. Sine of theta equals 4/5. Theta is 53. All right, so it's 4 times 4/5. So we said the moment at A due to B is, or due to tension, is 2 times T. And the moment at A due to tension at E is 4 times 4, which is 16/5 T. That's bigger. So the moment due to this tension at B is less than. Sweet. Oh, and the next question is draw a free body diagram of beam. How many unknowns? So yeah, let's just count them up. AX, AY, T. Weight is 5 kilograms, so I'm seeing 3. There we go. So I hope this helps. Yeah, we'll see you in class or in another video later.